Let's wrap up sections 5.2 and 5.3. After reading and working through the exploration, you should be able to write a null and alternative hypothesis in words and in notation for studies with two categorical variables, understand how one simulated sample would be created assuming the null hypothesis is true, be able to use a null distribution to approximate a p-value, and interpret a p-value or use it to assess strength of evidence to provide a conclusion to a test. You should also be able to calculate and interpret the standard error of the difference in sample proportions, either under the null hypothesis or without assuming the proportions are equal. Calculate and interpret the standardized statistic, calculate and interpret a confidence interval, and check the validity conditions to use the normal distribution. The dolphin therapy example is in your textbook and is summarized here. I'll give you a second to read through or remind yourself about the study. The null hypothesis is that dolphins don't help. We could state that statistically as saying swimming with dolphins is not associated with substantial improvement in depression, or there is no difference in true proportion of people with improvement in depression symptoms between those that swam with dolphins and those that did not. Notationally, we would say pi d minus pi c equals 0, or pi d is equal to pi c. The alternative hypothesis is that dolphins do help, so swimming with dolphin increases the probability of substantial improvement in depression symptoms, or the true proportion of people with improvement in depression symptoms in the therapy group is higher than in the control group. In notation, pi d minus pi c is greater than 0, or pi d is greater than pi c, where pi is representing the proportion of people with improvement. In the study, we saw 10 of the 15 people in the dolphin group show substantial improvement, while 3 of the 15 in the control group showed improvement. The difference in sample proportions, or our observed statistic, would be p hat d minus p hat c equals 0.467. If the null hypothesis is true, and there is no association between dolphin therapy and improvement, we would have seen those 13 people improve no matter what, and the 17 people would not have improved no matter what treatment they were in. So the assignment doesn't matter, and we can just randomly reassign the subjects to groups to see what would happen under a true null hypothesis. That means we will have 30 cards. 13 of those cards will represent improvers, and 17 will represent non-improvers. I don't care whether the improvers and non-improvers were in the therapy or the control group to start, because the null hypothesis is that the therapy does not matter. After we have our cards labeled based on success and failure, we'll shuffle the cards and put them into 2 piles that are the same size as the original groups, so 15 in the therapy group and 15 in the control. Finally, once we've done our shuffle, we will compute the conditional proportion of improvers in each group and find the difference between those two. Here we see the original data labeled on cards. 10 of the 15 people in the therapy group on the left improved, while 3 of the 15 in the control group on the right improved. I really don't care about what group they were in to start. All I care about is whether they were a success or a failure. So I can shuffle up the cards, and now I see 40% improvers in my new therapy group and 46.7% of improvers in the new control group. The difference in proportions using the same order of subtraction previously, therapy minus control, is negative 0.067. I can then plot that on my number line for the difference in simulated proportions. That would create one simulated sample, assuming the null hypothesis is true. We can then do this again and get a new conditional proportion of improvers in each group, find the difference, and plot that number on my null distribution. Let's repeat that one more time. Shuffle the cards together ignoring what group they were in and just leaving whether they improved or not on the card. Find the difference in conditional proportions and plot that number. Of course, we need more than 3 dots, perhaps closer to 1,000. Remember, our observed sample proportion was 0.467. Let's see how likely that is. My null distribution is starting to take shape. Only one of these simulated statistics out of the 30 seen here was large or larger than our observed difference in proportions of 0.467. So the p-value from these 30 simulated samples would be 1 out of 30, or 0.03. Instead, why is this distribution centered at 0? Because we assume the null hypothesis is true, or that there is no association between therapy and improvement, or that the conditional proportions are equal between our two groups. What would each dot represent? Each dot would represent one simulated sample, or the difference in proportion of improvement between the therapy group and the control group, assuming the null hypothesis is true. Remember, the order of subtraction remains therapy minus control in each of these simulated samples. The area highlighted in red here on the right-hand plot would be our p-value, or would represent the area of the p-value, the proportion of samples at or beyond our observed statistic of 0.467. It happened in my simulation. I had 13 of my 1,000 results with a difference of 0.467 or higher, for a p-value of 0.013. Let's interpret that number. There is a 1.3% chance of seeing the proportion of patients experiencing improvement in their depression symptoms in the therapy group of at least, meaning more extreme, 0.467, our observed result, higher than in the control group, if there is no difference in true proportion, or if the null hypothesis is true. As far as the conclusion, that p-value gives us strong evidence against the null, and we can conclude the alternative is true, that swimming with dolphins increases the probability of substantial improvement in depression symptoms. Let's go through the theoretical test. We would look at our overall p-hat of 13 out of 30, or 0.433, to calculate the standard error of the difference in proportions under the null hypothesis. In your calculator, you should get 0.181 by plugging in those values. I would say, on average, each difference in proportion, assuming the null hypothesis is true, is 0.181 away from 0, the null value. Then add context. Our standardized statistic should be 2.578, or the observed difference in proportions of 0.467 is 2.578 standard errors above 0. To create a confidence interval, I would need to recalculate the standard error without assuming the proportions are equal. In doing this, you should get 0.160 as your new standard error, or on average, each difference in proportions is 0.160 away from the true difference in proportions, the parameter. A 95% confidence interval would then give us 0.1538 to 0.7795. You could interpret that in one of two ways, either by stating how much higher the therapy group is than the control group, or by giving the order of subtraction, therapy minus control, in your statement. Finally, remember that intervals and tests still relate. I got a p-value of 0.013 and a 95% confidence interval of 0.1538 to 0.7795. Is it plausible that there is no difference in true proportion? At the 5% significance level, no. 0, the null value, is not included in the 95% confidence interval, and we reject the null hypothesis at the 5% significance level since the p-value is less than 0.05.